The focus is basically going to be on supervised learning. I'm actually going to have a recap of what we did the last time we met. I actually introduced you to what I call Introduction to Machine Learning, where actually I provided some background. Then I think we also focus on the types of machine learning, where we have the supervised learning, unsupervised learning, reinforcement, and the like. So today's lecture, we actually focus on one of the types of machine learning that we actually call supervised learning. Now, because we got several algorithms that we use under supervised learning, we specifically, the focus is basically going to be on decision tree. Okay, so in the outline today, going to talk about basic concepts of decision trees, which is one of the algorithm in the supervised learning. Then we're going to talk about decision tree induction. Okay, so I think I'm actually going to kickstart today from application. Of course, I want to remind everyone of us that before we actually seek redress in machine learning, of course, there is this practical problem. Now, when you take a look at the application that I'm actually showcasing now, okay, we got some patients, that actually visited a clinic, and 17 variables have already been measured on this patient. We actually range from, the blood pressure, age, among other demographic variables. And of course, these patients were actually admitted into the emergency room, and they actually need, the hospital here actually need to take a decision on whether they should put some of the patients in an intensive care unit or not. Okay. And, we got a lot of factors that determine where a particular patient goes. Okay. Due to high cost of ICU. Okay. So there's some patients who may actually survive less than a month. And those kind of patients will actually be prioritized. So the major problem, like I said here, is, how can the hospital actually classify, the patient into an high risk patient and a low risk one. Okay, they need what I call it, they have been faced with a classification issue here. So, for them to be able to take a decision, just like what I said in my video, whether we're using statistics or the machine learning framework, we basically need to work on data. Okay, situation where they have some available data that have some attributes and label. What I mean by label, if there exists some form of output, of course, the type of machine learning that we're actually going to use in that regard would be a supervised learning. Supervised learning in the sense that you have a data point, we have, where you have attributes, you also have a label, which we call the output. To every input, you got output. In this kind of situation now, we have some patient, in the past, this is not the first time the hospital, we have a patient in emergency room. So they actually need to go through the record in the past, where um, the record of patient they've had in the past, where they've collected this kind of variables. And of course, they already know where they classify, those patient into. So since, the response variable that I call the outcome variable exists based on record, of course, that will require us using supervised learning. Okay, so that is one example. Another example that we can talk about now, in the United States and in the Western world in general, there's something that we call credit card. And you know what? Probably every day by day, the credit card company actually receive thousands of application for new cars. And you know what? It's not going to be all of them of the applicants that will be approved for that. Okay, I remember when I was getting my credit card as well. They basically gonna ask, so the time I was applying, they're gonna ask question about age, the marital status, the annual salary. They are standing there, the credit rating. They also want to see whether one has the ability to pay back, and among other features that they actually gonna collect their data on. So of course, the major problem before the credit card company is whether to approve or not. Okay, so which means that they basically need what I'm gonna say, a kind of a technical advice on how to classify the applicants, based on the features, based on the attribute they have that they've collected on them, on the applicant, to classify them into whether they should approve their submission or not. Okay, so here we're actually going to use a supervised learning here because they need to look at their record of those who have applied in the past, and of course the status. Okay, they can use that. Okay, so machine learning and focus, like human learning, from past experience. Human learn from past experience, even though computer do not have experiences. But the idea behind machine learning is that the computer system can actually be used to learn from data. And of course, the data in this case now will serve as past experiences. You get what I mean? And that was why I said using, going into their record. Of course, they basically going to see the data, or were collected on those applicants, before. I mean, if you're referring to the those who apply for the credit card, okay. And if you're referring to the patient, whether they should be classified into the high risk or the low risk, of course, they can actually use the data on record. So generally, I remember when I was explaining something about, during the introduction to machine learning the other time, when I said we already have answers, we have input and answers, and what we just want to do is to figure out, what is the rule, what is the target function. Okay, so the idea behind machine learning is just to is actually to use the algorithm to learn, the model, okay, the model that relates the input to the output, okay. And you know what, the moment we're able to learn that target function, application, we actually have a way to investigate its performance before it can actually be used to predict the values, okay, of a discrete class attribute, whether to approve or not approve in the case of a credit card application, an high risk or low risk in the case of, patient in the emergency room. Okay, so what we're trying to talk about here is based on that, the moment where the algorithm was able to learn the target function, we are called the model. Any new patient now coming into the emergency room, the model can actually be used to classify that. Okay, so this is actually we call that the supervised learning. Okay, and the supervised learning here, we're using it for classification. Okay, so like I said, if we want to do anything, we basically need data. I remember in one of my classes when I said uh, we live in a stochastic environment. Okay, we live in a probability space. Okay, and you know what? Uh, Living in the probability space where different things happens in different days, we basically want to take decision that we don't want to regret, right? And which means that requires our understanding of the environment we find ourselves. And of course, for us to have an understanding, we actually need knowledge. And we don't get knowledge without getting information, because the information we translate into knowledge. And you know what? The information itself is embedded in the data set, okay, and something needs to be done on the data to be able to figure out the information that at the end of the day we translate into knowledge. Now, which means we actually need data. Okay, that was why I was talking about the other time, the case of patient in the emergency room. We are the hospital actually have issue which where to classify them. Of course, they can check into their record and say, the patient they have in the past that actually came into the emergency room. They've decided on those ones, they collected variables that I call features on them, and they've already been classified. And because the output variable exists, of course, we can actually use a supervised learning. So when you're talking about the input variables, we talk about the attributes. Okay, in the case of the credit card, the other company, the other time, we talk about age, we talk about credit history, marital status, whether they have job or not, and so on like that. And of course, we have a class. The class is actually output. Okay, and the class here, because we want to do something about classification now. Okay, so it's going to be categorical with levels. And don't forget, the goal of a supervised learning that has to do with the classification is basically to figure out what is the appropriate classification model that I actually call the target function the other time. Okay, from the data that can be actually be used to predict, the classes of new, cases. You know what I mean? Okay, so that is a major goal. Uh, in this, lecture, basically going to use example on loan application. Let's assume, um, some, this particular credit card company, actually have applicants who have applied, for credit card. And you know what? They have been faced with whether to approve them or not. They basically need to check into their record. And let us assume that this is their record, the record of the customers they've had in the past. If you take a look at the customer number one here, it was young, he has no job, okay, and he has, doesn't have his own house, and the credit rating is actually fair. And eventually, it was not approved for credit card. Of course, it's not everybody that apply for credit card, that get approved at the end of the day. So when you take a look at this class here, the class here is actually what we call, that would denote as Y, okay, which is the response variable. You get what I mean? And because this actually exists, okay, because this exists, we actually going to use what we call a supervised learning. Okay, so this is a record of of the applicant. The credit card company has had in the past. They collected some attribute features like age, whether they got job or not, whether they hold out the credit rating, and of course whether they get approved or not. Okay, so we got 15 cases of that. Okay, so what we basically want to do is to identify, what the classification model is going to be from the data. Don't forget what we do in machine learning. Is basically to identify a model, okay, that can actually be used to perform a task. That particular classification model is basically going to be used on a new data, okay, is going to be used on a new data. But you know what? We're actually going to train that uh, on the existing, we're going to use an algorithm. Uh, we're actually going to train that algorithm with the existing data, okay? And from there, we're basically going to learn, the algorithm is going to learn, a classification model, okay, that can actually be used to perform a task, okay? And don't forget, we actually have a way to investigate whether the classification model or whether the target function that we intended to get, that we actually got at the end of the day, is fantastic. Okay, so like I said, in the case of a loan application, we basically want to use the model to do classification for future loans. I don't forget, he said that we said that we approve or we don't approve. You get what I mean? Okay, so this is an example here. This person here is not in the data. Okay, it's a new data. Okay, based on the data set that we have here. Uh, can we actually use the classification model that our algorithm learn from the training set of the data, okay, to make a prediction for an applicant that is young, he got no job, he got no house, like he doesn't own his house, and the credit rating is good. And what we basically want to do is to be able to classify this particular person into whether it's going to get approval or not. Okay, so I think I've talked about supervised learning. In supervised learning, when you take a look at the data in supervised learning, the response variable that we also call dependent variable, that we also call label, exists. Okay, we got situation where they don't exist. So if they don't exist, well, that is what we call unsupervised learning. Okay, in an unsupervised learning, of course, the output variable is not given. And in that kind of situation, we basically need to establish the existence of classes within the data, which we actually call the clusters in the data. Cluster in the data is more or less like you are giving some set of data, without output variable. You're trying to look at the classes of, classification. Okay, the numbers of classes you can have, that's going to be a difficult one, because you don't have access to label, you don't have access to outcome variable. Okay, so we basically need to figure out what is going to be the unique number of classes. Okay, that's for the unsupervised learning. But what we're dealing with now is a supervised one. Okay, so talking about supervised learning process now, we got two steps. Okay, we got what we call learning and we got testing. What do we mean by learning? When you have a set of data, the data will be partitioned into two. Okay, the first set is going to be called a training set, and the second one is going to be called a testing set. The training set, we actually want to ensure that the significant parts of the data is committed to training. Okay. Of course, there's no special rule for this. I've seen some machine learning experts using 80 to 20%, 80 for training, 20% for testing. And I've also seen people using 75 to 25 and even 70 to 30. Okay. So, but you got to make sure a good number of the largest proportion of the data set is committed to training. Okay, so no, the moment the algorithm, learn the model, okay, the target function from the training set. Okay, we don't immediately use their module for classification of a new variable. So what we do, we test the adequacy of the model from the, using the text sets. Okay, when you take a look at the text set, we already have the answers like in form of the label, in form of the output. Okay, so we basically we can try to determine what is the accuracy of this model. Of course, we have other metrics of measurement. Okay, so this is the if a diagram, depicting the two process, where we train the data, we learn the algorithm, we learn the model from the training data, and we're basically going to put the model to test. Okay, we're going to use the test data. Okay, but we're actually testing the model using the test data. Then we can now calculate the accuracy, okay, which is going to be the ratio of the number of correct classification to the total number of test cases. Okay, like I said, we also have other metrics of measurement that can actually be computed. Okay, so what do we mean by learning? By learning, we actually have a task that we basically want to conduct, like in the area of in application, credit card application. The task is basically to classify applicants into whether they're going to be approved or not, okay, for credit card. Okay, so which means we basically need to have a data set, okay, of set D, and we basically want to perform a task T. And of course, we should have a performance measure M, because the module that the algorithm is actually going to learn from the data, from the training data. We should have a way to investigate the performance. Okay, so if you take a look at the loan application, um, you know, uh, the data is the loan application data. The task is to predict whether a loan should be approved or not. And of course, the performance measure here is accuracy. Okay, the accuracy is like, okay, what is the numbers of accuracy, that you actually have in the total cases of the text data. Okay, so if you take a look, some of you, so we're talking about no learning, when we classify all features application, The accuracy here is 9/15. How do I get that? If I go back to the data now, okay, in the entire data, we got 15 cases. How many, yeses, yeah, do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that would be 9 out of 15, right? Okay, which is going to be 60%, right? But you know what? The 60% is very, very small. Okay, this 60% is just based on the entire data, right? And you know we're not going to use the entire data. You get what I mean? The data will be partitioned. You get what I mean? Into the splitting, sorry, into the training and the testing set. So we're actually looking for an algorithm, okay, a target function that would do a better job, than just 60%. Because what happened here is no learning at all. No learning is excuse me, when you look at the whole thing, okay, when you look at the whole thing, like if you are looking at the descriptive statistics, you have 9 years out of 15, okay, and what we basically want to do is to improve on that. So that one is based on the historical data. Okay, so we actually have an assumption of learning. Okay, we expect that the probability distribution of the training example should be identical to the distribution of the text. Okay, if the probability distribution is not the same for both training and the text data, there's going to be issue. Let me tell you, at times we realize that the assumption is often violated, okay, to a certain degree, except that strong violations will actually lead to poor classification accuracy. And that's the reason why we basically need to pay attention, okay, to that. So how can we actually overcome this? If we really want to achieve good accuracy on the text data, okay, the training example must be sufficiently representative of the text data. Just like what we have in statistics, uh, we we take a sample which is a subset of a population before we can actually say that, okay, the sample, before we can use sample statistic to represent the population parameter. Okay, we got to make sure that the sample that we choose is a very good representative of the population. So right here, the training example, the training data must be sufficiently representative of the text data. The moment is a representative of that, it means they're basically going to have the same probability distribution. Okay, so I want to go into decision tree now. Okay, I want to use decision tree algorithm. There's a difference between the decision tree algorithm and the decision tree model. I'm going to say that again. There's a difference between decision tree algorithm and a decision tree model. What we basically want to use decision tree algorithm to do is to figure out, decision tree model that can actually be used for the task. Okay, so that's what I mean. Okay, so like I said, the classification model is going to be called a decision tree. Okay, so these are data again. Okay, now looking at this data now, if we want to use a decision tree, when you have a tree, right? We got a node, we got a leaf, right? In a tree. Okay, so what is going to represent a node is going to be the attributes. Okay, the attribute is going to be the node. Okay, what I mean by the attribute now, like in statistics, we call those attributes features. We also call them independent variables. Okay, so they're going to act as a node, like age, uh, whether he has job, own house, credit rating. So those are the node, right? Then the leaves now are basically going to be classes. Okay, they're going to be classes. Okay, when you take a look at this guy here, You're going to say yes or no, yes or no, yes or no. That is the classes. Now, for instance, I'm going to walk you through. This is an example of a decision tree. Decision tree is not unique. We could get different kind of decision trees for a particular problem. We actually have a way to identify uh, the one that is the best that we're basically going to use for a particular task. Now, if I decide to start with age, don't forget, age is part of the historical data that we have. And this age is categorical, or categorical in the sense that we got young, we got middle, we got old, right? The numbers of young is 5, the numbers of middle is 5, and the numbers of old is 5. And that was why when I wrote age now, there are 3 levels of that. The age here is categorical, young, middle, old. Okay, so if I now go into another attribute, has job or not, or own house. Okay, so has job. Okay, there are 2 levels. In a has job, okay, true or false. 2 levels in your own house, true or false. Okay, basically like probably 3 levels in credit rating. Okay, fear, good and excellent. Okay, so when you take a look at this guy now as job, okay, it has 2 levels, true or false. Own house, 2 levels, true or false, and credit rating, fear, good, excellent. Okay, so this one of the example of a decision tree, right? Okay, so when you take a look at this guy now, some of you may be wondering, how do I get 2/2 here? Now, what we're trying to say about 2/2 that we have here now, is more or less saying that, okay, I got somebody, one of the applicants that applied for credit card, to this credit card company is young, okay, and he has job, right? Okay, when he has job, okay, now yes means it was approved. Now let's now go into data now. We're going to look at young, he has job, and let's see how many let's look at the yes. Okay, this is young, 1. Okay, okay, this is young, true, he has job, right? Let's go to the class. Oh yes, it was given. Now let's go on that one, young, he has job, true, right? And yes. So when you take a look at that, we only have 2 situations. So which means the 2 people, 2 young applicants who actually have job, okay, at the end of the day, they were considered for the credit card. Okay, that was why I said 2/2. Okay, now when you want to start from this part, young, so no job, and no here means it was not given, and we got 3/3. Let's take a look at that. Young, force, no job. Okay, young, force. Okay, young, force for job, and it was not approved. 1. Okay, this is another one. 2. This is another one. So making 3. Okay, that was why you got 3/3 here. Okay, so if you do the same to middle age applicant, own house, true, and it was considered, that was 3/3. If you go back to the data, middle, true, yes. Okay, so okay, middle, true, okay, yes, okay. So if you take a look at that, give me 1 second. Okay, middle, own house, true, right? Middle, own house. So let's see. Okay, middle is right here. Middle, right? Own house, true, right? So if you take a look at this, right? Middle from number 8, number 9, number 10, the old house, right? True, true. And they were what? They were considered, right? That is 3/3. Okay, that's what you see here. Now the same thing also go with the others. Okay. Now, this decision tree here is not unique. We could have as many as possible decision tree. We have a way to pick one out of the decision tree at the end of the day. You see what I'm still going to discuss later. I'm going to that I call entropy. Okay, where we're going to consider information gain. Okay, now if I want to use this decision tree here to predict like a new data now, it's a new applicant, right? Okay, it's young. Okay, it doesn't have job. It doesn't own his own house. The credit rating is good. How do I get no? Okay, now let's take a look at this. Young, right? No job, right? False, no job, right? Okay, now what is it? What is it? What is it? The class, what is the response? That's no. Take a look at that. So that's why we're going to say, oh, this guy is not going to get approval. Okay, based on this decision tree. Okay, I want to take note of that. Okay, so the question now is decision tree unique? I'm going to say no. We could have as many as possible trees, just like what I said. But we actually want a smaller tree, an accurate tree, just like in linear regression, you know, we normally want regression with few numbers of parameters. Okay, we don't really want a complicated model. We actually need a model that have a fewer numbers of parameter and that is going to do a great job. You get what I mean? Okay. Now, so that's why I said finding the best tree is kind of hard. Now, this is another tree here. You know, this tree here is considering own a house and has a job, because I'm going to tell you this. When you look at those features that we have, somebody who apply for credit card, okay, you know, when the person own a house, it's an advantage. You know that, right? And when the person has a job, that's another advantage. And there's something I'm going to show you here. Own a house, if it is true that you own a house, right? You know, they consider them 6 out of 6. I'm going to show you now in the data. Okay, let's go to own a house. Okay, let's go to true. Okay, when it is true, look at our applicant number 4. When it is true that you own a house, it was considered. Let's go to another. That is number 1. Let's go to this number 2 now. Look at that. True. Yes, it was considered. True. Yes. True. Yes. True. Yes. True. Yes. If you count that now, 1, 2, 3, 4, 5, and 6. And that was why it is actually 6 out of 6. You see that now? So those who actually, based on the historical data, those who own a house, okay, they get considered, they get approved at the end of the day for their credit card. Okay, now let's go to those probably do not have a house, but they got job or not. If you take a look at this, false. Okay, they don't own a house, but they got job. Okay, is that they got job, true or false? So if you don't own a house, which is false right here, and you get a job, okay, true, then yes, 5 out of 5 means you're basically going to be considered. Let's take a look at that in the data. You don't own a house, but you got a job. Let's see. Okay, you don't own a house. Okay, but you got a job. Let's see. Okay, now look at applicant number 3. It doesn't own a house because under owning a house is false, but you get a job. Yes, it was considered. That's number 1. Okay, so let's look at another one again, false, where it doesn't. Now take a look at this guy now. It doesn't own a house. Applicant number 13, it doesn't own a house, but he got a job. What will happen? Yes. Applicant number 14 doesn't own a house, but he got a job. What happened? It was considered. So that was why, uh, you know, so that's going to be 5 out of 5. Let's see. We're going to count it down. We're going to count it now. 1, right? 2, right? Let's go. 3, false, true. Okay. That's 1. Let's see. Another 1. Okay. So you can see that now, right? Okay. So that was why you actually got auto Sunday. Now, if you want to make use of, let's say for instance, I want to decide on this algorithm now. Okay. There's another thing. Oh, there's another thing I'm gonna let you know here. It doesn't own a house. If you take a look at it, it doesn't own a house, but it got a job. It doesn't own a house. It doesn't have a job. Oh my God, that's a double tragedy. Let's take a look at this. False, false. No. How many times? Let's go back. It said 4 times, right? We're gonna see now. 1, false, false, no. That's number 1. False, false, no. That's number 2. False, 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 no. That's number 3. False, false. You can see that, right? So false, false, no. You can see that, right? Okay, so you can see this guy here. Okay, so if you want to decide on this algorithm now, so this is what we can do. Okay, the each path from the row to a leaf is a rule. I just wanted to know that. And what we basically want to do, a decision tree can be converted to a set of rules. Now, we want to consider owning house. Okay, if it is true, and the class is you are considered for the loan. We know the 6 out of 15 here is the total number of years. Those out of 15 applicants, based on historical data, okay, 6 were actually approved, right? Now, the 6 out of 6 is basically the guy here that I explained the other time, right? Now, when own a house equal to false, which means, the first one here, we actually come from here, right? Now, the second one here, we actually coming from here, right? Look at that. Look at the travel. False, okay? As a job, true. Okay, the class is yes. Okay, so that will occur 5 out of 5. And you know what? The 6 out of 15 here, this is going to be 5 now out of 15. If you look at the trend, 6 out of 6, 6 out of 15, and 5 out of 5, 5 out of 15. And here this 4 out of 4 here. This is going to go down to 4 out of 15. The R software or Python can actually get a result. But what I'm trying to do here is just to explain, the rationale behind, or to unravel what is behind the scene. You get what I mean? Okay. So if we have different kinds of decision trees, like, and we actually want to identify which one is the best. This is an algorithm, like a decision tree learning algorithm, like a code. But I'm going to walk you through something now on how we can actually choose. Okay, there's something that we call entropy. Okay, but before I go into entropy, I'll first, talk about, if you have 2 different kinds of decision trees. Okay, take a look at this. This is a decision tree. This is another one. In this decision tree, this only consider age, right? But in this decision tree, this only consider owning house. Now, if you take a look at this guy here, age, young, okay, out of how many people do we have we have 5 young people, right? How many of them get approved? Only 2, right? Yes, yes. You consider only 2 out of 5, which means 3 is no. Okay, that was why you got that number is 3 for no, 2 for yes. You do the same thing for middle and hold. Okay, this is one algorithm. If you take a look at this algorithm, you know, this is like very close to take a decision. Okay, which means I'm expecting the entropy to be kind of very high here. The entropy is actually what we call the when there is a high degree of disorderliness. You know, inference is very hard to take when the degree of disorderliness is very high compared to this guy here, this O'Grady. You know, what this guy is trying to tell you here is that the moment you own a house, okay, surely you are likely going on. You can see 6 was actually considered. Okay, we're here. When you own a house, okay, the number of people that was not approved for credit card is 0. And if you don't own a house, okay, if you don't own a house, okay, if you take a look at, because if you compare this guy and this guy here, you're basically going to see you have 6 in general, right? Okay. Now, what I'm trying to say is, in essence, is that if you take a look at this across 6, right? If you take a look at what I have here, this is going to be 9, right? 2 plus 3 plus 4 is 9, right? 3 plus 2 plus 1 is actually 6, right? Okay, so, but if you take a look at this, it's also 6, this is 9. But when you take a look at this, when you own a house, okay, surely you will be considered, okay? If you don't own a house, okay, then you will not. The 6 people were not considered, is only 3, because if you don't own a house, there's possibility you got a job, and that was why yes equal to 3 here. But let's take a look at this. Own a house, true. Let's see. We're gonna see own a house, right? Under true, right? 1, yes. 2, yes. 3, yes. 4, yes. 5, yes. 6, yes. Look at that. When you own a house, okay, then the 6 people that own a house actually get considered. Look at that. Okay, that is why. So a 0 out of them was not considered. It means all the 6 people that hold a house, they get approved. Now let us now look at those that did not hold a house. How many got approved? It's saying 3 people that didn't hold a house. So let's go back. Okay, we're going to look at own a house. We're going to look at under force. Yes, let's see. Force, yes, that's number 1. We're going to keep going. Force, yes, that's number 2. Force, yes, that's number 3. And that was how you got this 3 here. Okay, and when you take a look at those 3, okay, they don't own a house, but they got a job. Look at that. They don't own a house, but they got a job. Okay, let's see again. They don't own a house, but they get a job. So which means the reason why we got 3 here is because they don't own a house, but they got a job. Okay, so take a look at that. Now, if we're to choose between this algorithm and this algorithm now, okay, I'm actually, we're going to choose B, but I'm actually going to show you as we're going now, the reason why we choose B. The information gain here will be higher than the information gain here. Okay, so that was why I said B is seems to be better, but you basically going to see. Okay, so how we decide on B, we're actually going to consider what we call information theorem. Okay, the information theorem actually provide us a mathematical basis, for measuring the information content. Because right here, this decision tree contain information, this contain information, and you know what? The one that will lead to more information gain is the algorithm that we basically going to consider. Okay, so I will quickly go into the formula now. So which means we need to find entropy. And this is a formula to find entropy. Okay. And don't forget the entropy is actually is a measure of the degree of disorderliness in the data. The more the data is disordered, okay, uh, the more it should be very hard to take a decision. Okay, now I'm going to walk you through that now. So this is an example. A situation where you have data set where the label is have a 50% positive and 50% negative. Okay, which is going to be 0.5 for the probability of positive is going to be 0.5, probability of negative is going to be 0.5. Okay, now if you want to find the entropy, when you take a look at the formula, it's just going to be negative summation of the probability of CJ log of 2 probability of CJ. So what I'm basically going to do is like, oh, this class, I got 50-50, right? So I'm going to do minus 0.5 times log 2.5 minus 0.5. So when you do that, that is going to give you 1. Now, what if in a situation where it is not 50-50? This situation is very dicey. This is the entropy here is so high. Look at that. The entropy is high because it's a 50-50 situation. Prediction, classification tasks will be difficult to do here. Now, when I go to 20, when the positive is 20, where the probability is 0.2, and the negative is 80, which is 0.8. When I compute that, you can see it's going down, right? When it is 100% positive and the other one is negative, then the entropy is going to be equal to 0. But you know what? Number 3 here is not possible because we live in a stochastic environment where we cannot all be in the same class, right? So, and I said here, as the data become purer and purer, okay, here is becoming purer and purer, the entropy value will become smaller, okay? And which is very useful to us, but not as this, this is not possible, okay? Okay, so that is a formula. So, this is, like I said, that is a formula for entropy. If I now want to calculate the information gain now, okay, it's going to be the general entropy D minus a particular entropy. So this entropy here, we actually go with the attribute. Okay, don't forget, we basically want to select the best decision tree, right? Okay, well, and so how are we going to do that? Then each decision tree, we need to compute what I call the information gain, which can be got, we can actually compute that using this formula. Excuse me. So we want to choose the attribute with the highest gain, okay, to split our current tree. Okay, so I'm going to have a kind of demonstration here now. Okay, mathematically, okay, so how we do that? Okay, I'm basically going to walk you through that now. This is the data set, right? What is the number of yes, right? 6/15. And what is the number of no? Oh, sorry. The number of yes, let's count that again. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, the numbers of yes is 9 out of 15. And the number of no is 6 out of 15. So we're going to compute the general entropy. Take a look at that. Okay, this is more or less very close to 1, right? Which is telling you the degree of disorderliness is kind of very high, right? Okay, now take a look at this. 6 out of 15 log 2, 6 out of 15 plus. So we can first compute that. Now the next thing we're basically going to do is we look at the entropy, our attribute. Okay, like hold a house. Okay, the hold a house, for instance, I'm basically going to compute the D1 and the D2. Okay, now in in a house, in a house, you basically if you count the number of force, let's see that 1, 2, 3, 4, 5, 6, 7, 8, 9. That's why you have 9 over 15. And the numbers of true in our house is 6 over 15. Okay, now we need to calculate the entropy for that particular class. Okay, now if you want to calculate the entropy, for that, you're basically going to put into consideration this guy here. Okay, you're going to put into consideration that guy. And what you're basically going to use, give me one. I think I've showed you before. I'm going to go back to that now. Okay, right here, we're going to use this guy here. Okay, for the true, okay, for the false. And if you take a look at what I have here, okay, for no, okay, you're gonna, for this guy here, take a look at this guy now. Okay, what is the total? Is 0 plus 6 is 6, right? Okay, so when you take a look at when you had him, or when this guy is gonna be is 0 out of 6, okay? So it's gonna be is 0 out of 6 log 2 is 0 out of 6 plus, okay? And then we take a look at this, 6 out of 6 log 2, 6 out of 6. That should give you 0, right? When you do that. So that is why you have 0 here. Okay, that's why you have 0 here. Now, if you want to figure out this one, then you're going to consider the one of yes, right? You're going to consider the one of yes. Okay, you fall for do 6 out of 9, because 6 plus 3 is 9, right? 6 out of 9. Okay, I'm sorry, 3 out of 9. Yeah, you can, it's the same. You can do 6 out of 9. Log 2, 6 out of 9. Okay, plus, okay, 3 out of 9. Okay, log 2, 3 out of 9. Okay, then you multiply that by negative, and that will automatically give you what you have here. Okay, I'm going to say that again. How do I get 0 here, and how do I get this guy here? I'm going to say that again. I'm going back to whole new house. Let's go back. Can you see now? Okay, so this is it, right? I want to consider the probability of being in a class no and being in a class yes. I want to calculate the entropy for each of that. Now, if I want to calculate the entropy for this guy now, okay, the entropy for this guy now for true, okay, is going to be for true no, it's going to be 0, right? Out of the total, out of 6, log 2, 0 over 6, right? Then plus, okay, 6 out of 6, log 2, 6 out of that. So that's going to give you 0. Now, for this guy here, okay, 6 out of 9, log 2, 6 out of 9, plus 3 out of 9, log 3 out of 9. You know, multiply by negative, that's basically going to give you this guy here. You can try that. At the end of the day, then you calculate the entropy for owning house. Now, you do the same thing for H. If you want to do H, okay, you can actually create another table. How many young, how many middle, how many old. You can put that here, right? Now, age, young, middle, old, right? Okay, so now how many of this young resulted into yes? Okay, so let's see, 1, 2. That is this guy here. How many of this young resulted into no? 1, 2, 3. That was why you have this. Then I'm going to do the same thing to middle. I'm going to do the same thing to hold. And here I'm going to calculate the entropy. Now, let me I'll give me 1 second. If I want to calculate the, how do I get this guy here? What you're basically going to do is 2 over 5, okay, log, okay, log to base 2, 2 over 5, okay, plus, okay, 3 out of 5, okay, log to base 2, 3 out of 5. And whatever you get, don't forget, you're going to multiply by minus. That will give you this. Automatically, when you do it for this and this, it's like, take it, doing this on false and this. So it's going to give you the same entropy. Now, so which is what you are plugging in here for young. And that is what you are also plugging here, okay, for middle. Now, if you want to get this guy here, what you're basically going to do, you're going to come here, right? So don't forget 4 out of 5 log has to be log to base 2. Okay, 4 out of 5, right? Plus, okay, log, right? 1 out of 5, 1 out of 5 here, that will log 2, then 1 out of 5. Okay, don't forget whatever you're actually going to multiply by minus, and that will give you that. Okay, so that's exactly what you're plugging here. Okay, when you do this, you're basically going to get that guy. And how do I get 5 over 15? 5 over 15, of course, don't forget we got 5 young, 5 middle, and 5 old. Okay, so that is what you're going to do. Now, I've gotten, entropy for whole house, entropy for age. Now, what I'm going to do now is to calculate information gain. Now, if I want to calculate information gain now for age, okay, gaining information for age, you know what I'm going to do? I'm basically, I'm going to use the general entropy. Give me 1 second, and there's something I'm going to show you in the formula so that you can see what I'm using for information gain. Is this guy here. Look at that. The general entropy minus the specific entropy of a particular attribute. You get what I mean? Okay, so, and that is the reason why here, if I want to calculate information gain for age as an attribute, okay, I'm actually going to use the general entropy, and I'm going to subtract the one I got for age, which is what I'm doing here. And information gain using the content in the age actually is this guy here. Now for whole house, okay, it's going to be the general one minus the one I got for the house. Okay, so I wanted to take notes of that. Give me 1 second. Okay, thank you so much. I think I'm kind of back now. Okay, so we're gonna do the same thing for her as a job. Okay, you know, for her as a job, I didn't compute that here. You can follow what I did, so that you'll be able to find the individual entropy that will give you this. You can do that as an assignment anyway. When you subtract from this guy, you have this guy. So I'm actually, we're going to calculate the information gain for the attribute. Okay, don't forget, in the data set, we got for attribute, okay, age, owning house, as job, credit rating. So we're going to compute the information gain for all of that. Okay, so right now, we're going to look at the largest one. And as you can see, owning house has largest amount of information gain. And that is the reason why a owning house is going to be the best choice for the roots. Okay, if you want to have a tree, you need a root. We don't just use any roots. The root here is basically going to be one of the attributes So we're talking about it's more or less like own a house. Is an important key variable. Get what I mean? So that's why we actually we're gonna choose that. Okay, so own a house, and that is the reason why the final tree now it's gonna be own a house. Okay, so that is a final tree. Okay, that we basically gonna choose because it has the largest information. Okay, there's some other things in decision tree. Okay, uh, handle continuous attribute. So probably the next lecture we're going to talk about the continuous attribute. I mean the continuous attribute. Probably talking about uh, the one we consider here. They are all categorical, right? They are all categorical. So we have a decision tree that can also be used to work on that kind of data set. Okay, so how do we actually avoid overfitting in classification? Because a tree can actually, overfit the training data. The other time I said the probability distribution of the training set, must be consistent with that of the test set. Okay, we don't want a situation where you have a good accuracy on the training data, but poor on the test data. Okay, that's not going to be fine at all. Okay, so and one of the symptoms here is, tree too deep. Okay, and too many branches. We don't want to have so many branches, and we don't want to have a tree to be too deep. Okay, and you know what? Some may actually reflect anomalies due to noise or outliers. Outlier, according to Benkamp in 1982, is that a point that is not consistent with the rest. You get what I mean? Okay, data point that is not actually consistent with the rest. Okay, so I think I'm going to tell you now there are two ways we can actually avoid overfitting using the decision tree. Number one is a pruning decision tree. Okay, how we can prune that down. We don't want a situation whereby, imagine you have a tree with one leaf. We basically don't want that. So we can actually place a restriction on the trees. You get what I mean? So I'm actually going to walk you through that in my subsequent class on how we can handle overfeeding. And another way to handle overfeeding is a random forest. Okay, so random forest is another standout classification model that has worked over time. So that's one of the way to also avoid, overfilling. This is where I'm actually going to stop today. When else we're going to meet, I'm basically going to walk you through evaluation of classifiers. Is there anyone who need clarification before I go today? Is there anyone? Okay, I think someone is chat with me now and it said everything looks good. But you know what? If there's anyone who need clarification and you cannot ask question now, I need you to send a message to my email. Okay. At this point, this way I'm actually gonna stop. Make sure you stay safe and have a lovely day. Bye for now, everyone.